Okay, I'm gonna keep doing this. I'm gonna keep using code spaces, so I'm in Linux. But first, I want to demonstrate or some of the people on my on the Discord server figured out a way to get this to work sort of nicely on Mac OS. But there's a few things we need to change, and so because of that, I'm just gonna stick to code spaces. But I'll just show that really quick. If I where's clone the repo, this one. Um, Look at that. Okay. Um, and then do this. So I'd already been playing with this. Okay. Um, what? Why is there nothing here? Oh, there we go. Okay. So like for example, this one, which did a write syscall to standard out, and then this did an exit syscall. If I were to do, am I in the right place here? Okay. If I were to do this, which is the compile command, we need to compile for Mako, whatever this is called, 64, because it's on Apple Silicon. If I do that, except for I didn't want to do hello, I wanted to do hello proper, and then hello proper exit dot oh. That'll work. We'll have the object file. And then if I try to link it, which is this command, except I want to change this to hello proper exit and this to hello proper exit. It will have this error, right? So to fix this, instead of doing this, you need to use the lia command rsi rel message. And the reasons for this aren't entirely clear to me, but sort of makes sense. And now if I try to link it, it works. And so I have over here now there's this executable. And if I now run that executable, I get invalid syscall, right? And the reason for that is because also on macOS, the syscalls are different numbers, right? So we're using 1 here for write and 60 for exit. It's different on macOS. This becomes OX2000004, I think, and then this becomes the same thing, but 1. So then now if we recompile it and then relink it and then call it, it says hello world and exits properly. Oh, and you can't even see it because my head is in the way. Check it out. There, now you can see it. In case you didn't see that, I just I recompiled it, I relinked it, and then I ran it. And sure enough, it worked as expected. So that's cool. That's running natively on my Mac. This isn't, I'm not SSH'd into anything. So now, that said, this is kind of a pain to change things. I want to be able to just follow along the book and have it work. So I'm gonna jump back into my code space. Why do I have solid start code spaces? Is it because I've contributed? I have no idea. Let's try my code space. Meantime, I'll pull up my book and make this more like that, maybe. Cool, we're in. And we should still have the oven. What just happened? Yeah, cool, it saved all my. Alright, we still have all those weird errors, and it's being really slow, but it's alright. So these all work. I think we were working on this last time. But yeah, we learned about all these like jump commands and stuff like that. We'd written this. I don't know if I'd ever had us run this, because now it's running off to function calls. So maybe we should try to compile and run this. Let's do it. Wasn't I using like the built-in NeoVim terminal because it was easier? So I'm gonna say, what were the? It was like NASM. Oh yeah, they're still in my history. Check it out. Here we go. NASM. Yes. Okay. But except for instead of that, I want the print RAX as a -o print RAX .o, and that worked. And now we have the object file right there. And then I want to where's my linker command? Here we go. Oh, that's all there is to it. Okay. Print RAX, and this can become print RAX. And now we have this executable. I'm gonna try to run it. Print RAX. Sure enough, we got that. It's what we wanted. Oh, how did we escape out of this? Command / command, or not command, control / control N, I think. Yeah. Cool. This is, yeah, can you explain to me what we were trying to do here? Let's try something harder. Let's output the RX value in hexadecimal format as shown in listing 2.5. This is, oh, so that worked. Because this is the hexadecimal format, because this is a hexadecimal number. So let's dig into this and try to figure out how it works. So these are, I guess, just like the digits in hex. We stick it in codes, which is constant. And then we move this guy into RAX, okay? Then we set RDI to 1, which means we're gonna do no, that doesn't mean anything. What does that mean? RDI to 1. Why do we do that? He doesn't really explain what each step of this is doing. RDI is like the first, yeah, it's like the first argument position for a syscall. But not RDX, RCX. I'm not sure like why this is all happening. Do you understand what this is doing? That's not what I wanted. Oops. Why isn't this copying? I have to do it like that way. What? Okay, copy to clipboard. Copy. What? Some weird code space thing? you read this from an image? That'd be impressive. Whoa, he's reading the image. That's cool. Okay, initialization. Here we go. Loads a large hexadecimal number into RAX. Okay, such as registers for a loop. RDI is set to 1. Oh, because that's for standard out. Because we're gonna, I guess, do we're gonna do a write somewhere. Here, no? This makes it write, and then we syscall. Okay, and then RDX is set to 1, number of bytes to write, because we're doing one at a time. RCX is set to 64, used as a counter. Okay. Loop. The loop iterates over the bytes of RAX. So we start, this is like a label for our loop, and then we push it onto the stack. Then decrease RCX, which is our counter, by 4. Shift RAX right by CL, which is the lower 8 bits of RCX. What is RCX? This guy, the counter. Okay. This was like that like the shift thing that was talked about in here. Here. We found the difference. Like one of them preserved the sign and one of them didn't or something. And then masks RX with OXF to isolate the last 4 bits. I'm not sure what that means. We'll ask in a second. And then prepares the for syscall array to the it uses the bits as an index to the codes array to get a character. So we're loading into RSI codes offset by now what's in here. Okay. Continues until RCX is 0. That's this, right? Okay. J and Z. What specifically is J and Z? I know it's one of the jumps, but they're all like different. Jump if not 0, maybe? Yeah, look at that. Jump if not 0. So if RCX is equal to 0, I guess, then it'll skip this loop and it'll just exit. So that largely makes sense. This and thing I don't totally get. A bitwise AND operation between the value and the RAX register and the hexadecimal value OXF. Purpose, isolate the last 4 bits. The operation clears all bits in RAX except for the last 4. This effectively extracts the last 4 bits of RAX. Okay. If RAX contains that, after that, it'll contain just OX8. Okay, which is the last 4 bits. Yep. This is used to index into the codes array to get the corresponding. Okay. That makes sense. I think I get this now, largely. Probably couldn't have made it up on my own, but it's interesting, for sure. Alright, let's keep going with function calls. Routines, make this bigger. Routines functions allow one to program a piece. Sorry, let me put my phone on Do Not Disturb. Okay. Where was I? Routines functions allow one to isolate a piece of program logic and use it as a black box. It is a necessary mechanism to provide abstraction. Abstraction allows you to build more complex systems by encapsulating complex algorithms under opaque interfaces. Instruction call address is used to perform calls. It does exactly the following: push the instruction pointer, jump to the address. Okay. The address is now stored in the stack, the former RIP contents. Sorry, the address now stored in the stack, the former RIP contents, is called return address. Any function. Oh, so that's where you'll return to. That's interesting. So like we push the address of where we are onto the stack, and then we jump over to the address wherever we're gonna go, do a bunch of stuff, and then we need to return back to where we were, and so we'll just pop the instruction pointer. No. Any function can accept an unlimited number of arguments. The first 6 arguments are passed in RDI, RSI, RDX, RCX, R8, and R9. Same for syscalls, right? Respectively. The rest is passed onto the stack in reverse order. What we consider an end to a routine is unclear. The most straightforward thing to say is that RET instruction denotes the function end. It is semantically equivalent to pop RIP. So you pop the top of the stack back into REP, so the return address. That's really interesting. Apparently, the fragile mechanism of call and RET only works when the state of the stack is carefully managed. That makes sense, because you need to have the return thing on the top and you pop it off. Let me lower my camera. Okay. One should not invoke RET unless the stack is exactly in the same state as when the function started. Otherwise, the processor will take whatever's on top of the stack as return address, and use it as the new RIP content, which will certainly lead to executing garbage. Now let's talk about how functions use registers. Obviously, executing a function can change registers. There are 2 types of registers. Callee saved registers must be restored by the procedure being called. So if it needs to change them, it has to change them back. These registers are callee saved. RBX, RBP, RSP, R12 through R15, a total of 7 registers. Caller saved registers should be saved before invoking a function and restored after. One does not have to save and restore them if their value will not be of importance after. All other registers are caller saved. These 2 categories are a convention. That is, a programmer must follow this agreement by saving and restoring callee saved registers, being always aware that caller saved registers can be changed during function execution. Okay. I wonder if it says that in that table of mine. This one. Oh yeah, check it out. When calling a function, might be changed, will not be changed, will not be changed, might be changed. See, this is really handy. Whoa, it even has all these down here. This is super handy. Whoa. Oh, look, here's all my jumps. Or not all of them, I guess. It says basic. Yeah, cool. Call, return, push, pop. That's really cool. Okay. We read that. Okay. No. A source of bugs. A common mistake is not saving caller saved registers before a call and using them after returning from function. Remember, if you change these, change them back. If you need any other register to survive function call, save it yourself before calling. Some functions can return a value. This value is usually the very essence of why the function is written and executed. Sorry. For example, we can write a function that accepts a number as its argument and returns it squared. Implementation-wise, we are returning values by storing them in RAX before the function ends its execution. If you need to return 2 values, you're allowed to use RDX for the second one. So the pattern of calling a function is as follows. Save all caller saved registers you want to survive function call. You can use push for that. Store arguments in the relative register. Okay. Invoke a function using call. After function returns, Rx will hold a return value. Restore caller saved registers stored before the function call. Why do we need conventions? A function is used to abstract a piece of logic, forgetting completely about its internal implementation and changing it when necessary. Such changes should be completely transparent to the outside program. The convention described previously allows you to call any function from any given place and be sure about its effects. May change any caller save register. We'll keep callee save registers intact. Okay. Some syscalls also return values. Oh, that's interesting. Be careful and read the docs. You should never use RBP and RSP. They're implicitly used during the execution. As you already know, RSP is used as a stack pointer. All right. Sorry. The margins aren't the same on both sides of the page because it's like a real book. And so it's messing me up. On system call arguments. The arguments for system calls are stored in a different set of registers than those for functions. The fourth argument is stored in R10. Oh, so it wasn't the same, but they're similar. Okay. Well, the function accepts the fourth argument in RCX. The reason is that syscall instruction implicitly uses RCX. System calls cannot accept more than 6 arguments. Okay. If you do not follow the described convention, you will be unable to change your functions without sorry. You will be unable to change your functions without introducing bugs in places where they are called. Now it is time to write 2 more functions. Print newline will print the newline character. Print hex will accept a number and print it in hex format. Oh, cool. I love writing assembly. Keep my terminal open there. Let's add a new one called print call.asm. Why did that split? Can we get rid of that guy? What is happening? Oh dear, oh dear, oh dear, oh dear. Help, help, help. Okay, try that again. Oh dear. Find file. What was it? Print call. Okay. Here we go. Section data. It's gonna have a new line char, which is db10. 10, I think, is the ASCII code for the new line, right? So, this is the new line character. Thank you, Copilot. Okay. And then, actually, we don't really need comments. Then I'll say codes is a db0123. I'm actually going to turn Copilot off. Copilot disable. Thank you. All right, 1, 2, 3, 4, 4, 5. What is it? 6, 7, 8, 9. A, B, C, D, E, F. That's the same thing we did before. And then here comes text. So global start is the entry point, I guess. Print new line. Here's our function. It's gonna move RAX to 1. This is the code for the right syscall. Move RDI 1 so that we're putting a standard out, and then move RSI the new line char. This RSI contains the address to whatever we're going to be printing. Move RDX 1. This is like the number of bytes we're going to print, and then we do the syscall, and then we return. Looks like he's doing some like different annotation with the return. He's doing like this. I'm not sure why. We'll just keep it even. Okay. And then we'll make another one called print hex. We'll say move RAX RDI. Why? Why do we move RDI? Why? I'm not sure yet. Okay, we're gonna find out. Move RDI 1. So standard out. Move RDX1, which is the amount of bytes to write. So we are writing standard out and we're writing 1 byte. Okay. And then move RCX64. And this is where's my handy chart? RCX, what's RCX? RCX. It's the 4th integer argument. Might be changed when writing a function. Use freely. What is the RCX register generally used for? General purpose, okay. Loop counter, function arguments, shift and rotate, string operations. Okay. Okay. RCX64. And then we have the new iterate label, which looks like this. Iterate. Push RAX. Okay, we push RAX, I guess. Then we sub RCX4. So we are using it kind of as a counter. We're gonna subtract 4 from it. Then we're gonna SAR, which is like shift SAR register explain. Oh, it's not a register. Sorry. Sorry, I meant operation in assembly. It's not a register. Shift arithmetic right. Oh, so this is the one that preserves the sign. To the right. So we're shifting RCX by 4 bytes, which is 1 hex space, right? Okay. SAR. Sorry, not RCX. RAX by CL. Oh, okay, this is different. And then CL. What was CL again? And then what's CL? It's like part of one of the registers. It's the lower 8 bits of the CX register. Wait, what? Okay. And then we do the and mask trick thing. And RAX 0x. Oh, look, there's handy comments. How far are we shifting RAX? Was this? So I should write these in maybe. Push RAX. Save the initial RAX value. Okay. Shift to 60, 56, 52, comma, yeah, so on, down to 4, down to 0. That's what that does. Okay. CL registers. Oh, it's the smallest part of our CX, which has the counter in it. Okay. And then we do this. Clear all bits but the lowest 4 in RAX. I don't understand how we're moving. The thing I didn't understand why we're moving RDI into RAX initially, but I'm starting to suspect it's because, yeah, RDI is going to contain our thing that we want to print. Oh. Okay, so we move the thing we want to print into here. Set up for a write syscall. My line disappeared. Tell it we're going to print 1 byte. Set up our counter. Now, we save what's currently in RAX, okay? Then we, like, increment, let's really decrement our, because we're counting down with our looper, this RCX, I'm going to call him looper. Then we shift REX by CL, which is a little bit cryptic. We shift the whole thing by the smallest part of RCX. I don't understand why we do that. All right, anyway, for now. And then clear all bits but the lowest 4. That part kind of makes sense. Take a hexadecimal digit character code. LEA, RSI, codes, plus RAX. This loads into RSI. RSI. Is there something special about RSI? Well, anyway, the code's offset by RAX. And then move RAX to 1 so that we can do a syscall. And then we're going to push RCX. Because the syscall is going to break it. Oh, okay. And then we're going to do the syscall. We're going to actually go in and add. Oh, and then we'll pop him. Pop RCX. And then pop RAX. See line 24, because line 24 was this, where we push down, and then we'll pop him here. Cool. And then test RCX against RCX to see if it's 0, right? So jump if it's not 0, jump if not 0, iterate again. So we'll just loop this, and then we'll return otherwise. And then here's start. I'm not sure why you don't have like new lines and stuff in better places. Move RDI, our thing we want to print 1 1 2 2 3 3 4 4 5 5 6 6 7 7 8 8 9, or just 8 8. And then pop our no, sorry, we need the right spot. Call print hex, and then call print new line, and then move, and then it's just exit. Cool. How long is this video currently? 33 minutes. That's not too bad. How long is this next section? Sort of lengthy. Well, let me at least run our new file here. What's called print call. Print call, and then can we link it? It worked perfectly. We even got the new line. Now check this out. If I hadn't done the new line, according to my research, it should do the same thing without the new line, just as expected. Cool. I'll go restore that to where it was. Okay. And then get back my nice result. Cool. Awesome. This is really nice. I'm gonna commit. I wonder. I don't really want those files in my. Yeah, I don't really care, I guess, but just to make it really clean. Cool, we'll do that. And then now I will, sorry, wait, now let's try. Okay. Get status. Okay, yeah, get that. 2.4. Get push origin master. Awesome. And now repo. We have this cool file you can check out. It's also in the book, obviously. Yeah, I got some other stuff I need to do this morning, so I'm actually gonna just stop there. It's sort of a shorter video today, but maybe do a longer one tomorrow. What is it? Thursday? Yeah. All right.